I prepared a small demo, but I planned this demo to be hands-on. So normally I didn't imagine it will be in a room like this, but I think we can make with what we have. So this demo will require you to install a Pharo 9 image and to install CORMAS on top. So can you raise hands, the people who have their computers with them and who want to follow this demo? Okay, 1, 2, 3. Okay, good, perfect. So I will try to do it this way. Technically, the demo will not be complicated, so you will just load the code from GitHub, you will play with it a little bit, you will manipulate it, and we will see how it goes. So normally, this demo was going to be done together with Ernan, that's why I put his name there, but unfortunately, or fortunately, Ernan was invited for a very cool presentation in another building, so like that, I will be doing it myself. So first of all, the thing that you need to do is to create a new Pharo 9 image and to install CORMAS. And for that, you can go to, so you can either copy this metashell script or type it from the screen, or you can go by this link, github.com, CORMAS/CORMAS, and like that you will see is the CORMAS GitHub repository. And in the README, there are the instructions how to install CORMAS. So I will follow it here, so like that you can see. Yes, so when I click on the link, it opens the GitHub. And then I scroll down, you see this very nice README. And over there, you have 2 installation scripts. So you need to install the latest one, not the version, because the first one gives you the version 0.7. You need to install the version, well, the development version. Because today we did some important changes together with Milton. So I want you to have those changes. Oh, I will delegate this question to Cyril. What does EP monitor do? You know?
EP monitor, it's EPCA. It logs all the class creations, method creations, etc. And it's on my to-do list to add something to disable it when Metaselo is writing the code.
Yes.
Or maybe not disable it, but put it in another session or I don't know, so that it does not pollute your EPCA logs.
Yes, so I will repeat for maybe not everyone heard Cyril, and also from what Cyril explained me before. The idea is that it makes loading faster, and normally it should be integrated into Metaselo. So in the future, we'll just run Metaselo. But you can install CORMAS without that. It doesn't give any visible difference. Yes, but it's important. Yeah, the important part is you install the second one. So you don't include version 0.7. You don't include that part. Okay, I will do the same on my machine. So I create a new Pharo image. I use Pharo Launcher for this. Yes, very important, you must use the deprecated. You see, you go here in deprecated distribution, Pharo 9, and you give a name, some CORMAS demo. CORMAS demo. Okay, oh no, is it a French keyboard? No? Okay, CORMAS. Yes. You see, that's the problem. They gave me the computer with a French keyboard, and I always make mistakes. Okay. Why do I not have create image now? Where did the button go?
You have to open. You have to
Make it bigger?
Yeah.
Okay.
No. You already have an image with the same name exactly.
Oh, right. Okay. CORMAS demo 2. Okay, perfect. So while it is creating the image, it is done. Now I will open it, and I copy the same script here. Yes. I go like this, and I paste it here and I execute it. Okay. So while it is installing CORMAS, it may take 2 minutes. I will show you the model that we will be working on. So it is a very simple but interesting model. Yes. Oh, why do I have this presentation? I don't want this one. I want this one. Yes. So it is a very interesting and simple model. It is called the ESUG model. So it's the model that demonstrates the evolution of cooperation. It was not the model that was developed by us. It was in fact introduced in this paper from the year 2000. And but in our team, we use this model heavily because it really nicely demonstrates the different aspects of agent-based modeling. So, but I will do a very simple demonstration, so we will just implement the very basic things. So, yes, here you can see how it works, it's running. The important things, so the model consists of two types of entities. You have spatial entities and agents. So spatial entities, in our case, those are plants, and agents, they are foragers. And we have two types of foragers. So you can think of foragers as cows. For example, cows are eating the plants. Plants, they can only grow and be eaten. They're very simple things, and they are represented by their biomass, by the amount of biomass that they have. And foragers, restrained foragers, they eat a moderate amount of grass, and unrestrained foragers, they eat a lot of grass. So we will be seeing how the dynamics of these foragers, so for example, how do they compete for the grass? If we look for the grass or plants, so it follows these simple rules. It is only created once, it has a fixed location, so it cannot move, and we make sure that the grass does not die. So I will show you later how we make sure of that. It can also not reproduce, so grass is just a thing that is growing, growing, growing until it is eaten. Then it has no other behavior than to grow, and the only difference between grass and between the plants is biomass, so we don't have different types of the plant. Normally, we could implement the growth of the plant very simply. We could just say add one, add one, add one, so that it grows linearly. But in natural sciences, it's very common to use this kind of logistic equation to display that something is growing. You see it has the reproduction rate, the carrying capacity, and the growth factor. So the idea is that it makes sure that the grass at the beginning, it will grow faster, and then at the end it will stabilize and it will not grow so fast. So we will not have this enormous grass that is growing somewhere. Finally, the foragers. So these are the rules how the foragers are feeding. So first of all, at every step, foragers are burning energy because they need some energy to survive. And you can think actually of energy and biomass as the same thing. So basically, biomass is the amount of energy that the plant contains. So every forager has a catabolic rate, and for all of them is the same. It's 2 units of energy. So at every step of the simulation, the forager will be losing energy by 2 points. Then the forager always eats, and in every location when it eats, so it increases its own energy by the same amount as it eats. So if it eats 50 points of biomass, it means that it increases 50 points of energy. And the two types of foragers, so like I said, the restrained foragers, they eat a moderate amount, which is in our case 50% of the plant, and unrestrained foragers, they eat 99%. And that's why we put 99 and not 100, because we want to make sure that the grass doesn't die, because if you eat 100, it will disappear and never grow back. So yes, foragers, if the energy is 0, forager dies because, well, no more energy. If their energy is 100, they reproduce. And these are the rules of reproduction. So basically, they reproduce asexually. They don't need any partner to reproduce. They basically just create a new forager of the same type. So restrained foragers create other restrained foragers. Unrestrained foragers create other unrestrained foragers. When the forager is created, its initial energy is set to 50, and by the same amount, the energy of the parent forager is decreased. So basically, you can think that the forager that has energy 100 is splitting into 2 equal foragers. The new forager is created in any empty cell around its parent. Yes, and here you can see the class diagram that this model is represented by. So we have the plant. You see the K and R, those are the factors that we use for logistic growth, so to make sure that the plant is growing. And plant has some instance variable, which is biomass. Then at every step, we decide, so every step calls the function logistic growth, and like that, at every step, the plant is growing. And many plants compose the landscape. So in our case, the landscape will be composed of 27 by 27, I think. So you will have a grid of plants. Then on the other side, you have a forager. It has a catabolic rate of 2. The fertility threshold is the threshold at which it is reproducing is 100. And the harvesting rate and the energy. So harvesting rate, as you see for restrained forager, is 0.5, which is 50%. And for unrestrained forager, it's 0.9, which is a bit inconsistent with what I showed you before because it was 99%. But the idea still remains. And then the methods of the forager are to step, and during the step, the forager consumes energy, eats, reproduces, and dies. Reproduces or dies depending on the amount of the energy. Okay, so these are the slides to explain the forager. The only thing that I forgot to put in these slides is the rules by which the forager moves, which is an important thing. So basically at every step, forager looks around it, and it looks and it moves in any cell around itself if the cell contains enough biomass and if the cell does not have another forager. If around the forager there are no other cells, then it moves into a random location around itself. So now when you have CORMAS installed, hopefully, so you can look at your images and you can tell me if it worked. Did it work? Can you raise your hands if it worked? Okay, good, good, good. And for whom it is still installing? Okay, good. And for who has problems, issues, bugs? Nobody. Wow, that's amazing. I did not expect that. Yeah, so for now, we will have bugs. Yes. Okay, so we will wait until, is it close to finishing or should we? Oh, okay. Okay. So I think we can continue, and then, because I'm also preventing you from going to the hotel and going to the social event. So, yes. So, okay, first thing I will do, and also this is something maybe you should do in your images, because it's Pharo 9 and not Pharo 11, it does not automatically detect the SSH keys. So I will go to my settings. I will go to tools, because I will need to be using Iceberg, and for that I need SSH keys. Then software configuration management, Iceberg. Is it too slow? Is it too small? Should I make it bigger? Okay, I will make it bigger. Yes, credentials, SSH keys, and here we have Here we have SSH. I will put the public SSH and the private one. Yes. Okay. Now I open my Iceberg. So those of you who already installed CORMAS can follow me here. I open my Iceberg. I go to Add, Clone from GitHub, and I clone this ESUG model. So CORMAS, French keyboard, CORMAS ESUG/model. So this is for those of you who are not very familiar with Iceberg. If there are people who are not familiar with Iceberg, yeah, I will make it bigger because yes. Settings, appearance, medium should be good. And do you know if I can apply it to the existing Windows? Okay, I will do it again here. So yes, CORMAS ESUG model. You see owner name CORMAS, project name ESUG model. And I do OK, and it should clone it. After that, I find it in my Iceberg, and I open it and I load manually the ESUG model package. Here we go. Okay, so I will show you what it has created. But first, I will show you the standard process of creating models, because this is something that is currently not working, because I'm showing you the very, very beta version of CORMAS with many, many bugs. And it is also something interesting that I would like to show you. And by the way, I forgot to mention one thing, that during this demo, I'm also very interested to have your feedback on CORMAS and to collect some small bug reports. So for example, if you are trying this on your computer and you notice some things that are not nice, unpleasant, broken, buggy, you can please create an issue on GitHub on this CORMAS repository. And originally I wanted to ask you to put a label on your issue ESUG 23, so like this I will know where these issues come from. But I just found out that you cannot, because you need to be members of the repository. So sadly, you can create issues. I will see by the date where they come from. Okay, So you see, normally the idea, and this is something that exists in VisualWorks, but something that is currently broken in Pharo CORMAS, that to create a new model, as I told you during my presentations, we don't want people to work directly with the code. So just now we loaded the code from GitHub because we don't want to lose too much time. But people, when they create new models, when click on this new button, then they can enter the name of their model, let's say something blah. Okay, you see we have already some information that current project name, choose another name, but I don't want to, okay. Then here in this window, you are asked to enter your information. So for example, as author, I am Olex, and my email is something .author.com, okay. And now you see this created, now my window is already initialized as CM blah. So like this, I created a blah model. But you see where the bug comes. So when I click here, normally nothing happens. I don't see this. The class for each entity should be active because it would mean that the model was created, that I can open the class editor. But like that, I will probably need to close this window, then open it again, then click on open, and then I have this blah model which I can open. And you see now it shows me the simulation interface. So now this blah model exists. So I can click on programming, the class for each entity, and I can start adding entities. So for example, I can add a spatial entity such as plant. Here I add plant. Oops, planet, like this. Okay, and you see that's another bug that it doesn't update the view, but the plant was created. Because if I click on programming, open system browser, it shows me that, oh no, it didn't create the plant, you see. Oh. So like that, we will not continue with this visual interface, but this is just to show you that normally in original VisualWorks CORMAS, and hopefully soon in also Pharo version of CORMAS, there are two ways of defining models. There is the way of defining them through code, and also the way of defining them through graphical user interface. And together with Ernan, we are working on how to make a really nice user interface where you can make a lot of you can set the parameters, you can interact with your model, you can set pretty much everything except the behavior of the agents in the UI. So like that, we try to minimize the amount of code that people have to write. Okay, but for now, I will close this. And instead, we will load the model that was already predefined that we have just loaded from GitHub. And I click on open. So again, I will do it slowly so like that you can follow. In the main CORMAS window here, I click on file. I click on open, and I get this window here that allows me to select models from image, user models, or from file. And here I select on ESUG model. And then I click on OK, and it is loaded. Do any of you have problems with that? So because I hear that some...
Can you reshow in Iceberg
Yes.
how to load the model?
Sure. So in Iceberg, you open Iceberg. You click on Add. You click on Clone from GitHub over here on the side menu. Then you click on Owner Name. You know, maybe, can I do this? Yes. So like that, we will have more light on the screen. Okay, it should be better. Is it okay for the camera? Okay, good. So yes, you can see here you open Iceberg, you click Add, you choose from the side menu Clone from GitHub, and now you can enter two parameters. So you enter the owner name and the repository name. So these are on GitHub, these are the parameters that are here. You see in the link of GitHub, this part is the owner name, so your username, or in our case, the name of the organization, which is also named CORMAS. And the repository name is named CORMAS. But we load right now the other repository. We load repository from CORMAS organization. Wait, here, CORMAS organization. We load the ESUG model. So in that case, this one, this part is CORMAS is the owner name and ESUG model is the repository name. So you enter them here. CORMAS ESUG model. And when you click OK, and you can choose SSH or HTTPS. So if you have SSH keys, you can load with SSH like I did. If you don't have SSH keys, you can load with HTTPS. It should be fine, I hope, but it should work for loading, but you might not be able to commit. It works? OK, cool. So how many of you have already opened this view? How many of you have loaded ESUG? OK, you loaded. Good too. And the others, do you have problems? OK, who has problems? Can you raise hands? So like this I know. OK, one. Yes. What kind of problems? The Wi-Fi? Oh, OK. Yes. And the others like Cedric and. Yeah, I can come to you so I can see on the screen because I wanted Ernan to help me with this, but he's not here unfortunately. Yes. So if the model, yes, I forgot to tell you. Yes. No, where is it? Sorry. Yes. No, not that. So, can you show me in Iceberg? So the idea is that after you loaded the model with Iceberg, you must also double click on this repository and open the package and load specific package.
So where is it?
Yes, in the end, yeah, you double click. Yes, it's like that. I will show on the screen. Yes, so that is something that I did, but I forgot to comment on that at the beginning. So you see, when you load something with Iceberg in this method, so if you load it directly through adding through using the add method, the add button, you need to double click on this repository, and you see that the packages are not loaded. So I needed to load ESUG model package. I will show you the same example on the baseline of ESUG model package. You right click on this package. Here, right click. No. Right click like this, and here is the button load. So this allows you to load this specific package. Okay. So you need to do that with the ESUG model package. And once this is done, you go to CORMAS, file, open, and the ESUG model should be in the list. Okay, it works? Okay, good. And Cedric, it works? Perfect. So we're progressing a little bit. Okay, now once you have this model, so I will show you, you can click on programming, open system browser, and it will show you directly the implementation of the model. So you will see the ESUG model package. I will write here ESUG model to highlight only that. And you see the classes of this model. So it consists of the following classes. The classes that I showed you already on the UML diagram. So you have the forager abstract class, the two subclasses restrained forager and unrestrained forager. So depending on how much grass they will eat. The vegetation unit, this is the plant. And model class, this is the central class that we use to orchestrate the model, so that it will decide, it will hold the references to all these elements, to all these objects, to all these agents, and it will decide who performs the action after whom. So also the interesting thing is that if you look inside how these methods, how these things are implemented, for example, ESUG forager is a subclass of CM agent. So CORMAS provides these superclasses that allow you to define your own models. So, and for example, it uses the trait TCM located, and this trait contains, you can see here, all these methods for location, movement. So like that, the forager already knows what is the location, what is the patch, what is the, it doesn't know the notion of the plant, but it knows the notion of the cell on which it is located, and how to look at its neighborhood, how to move to a neighboring cell, things like that. So you can see here by the protocols that the agent has the, I will show you here. So there are some important methods in CORMAS. One important method is the initializing method. So, but not this one, is the, we call them init. You see, it's the legacy names. Where is it? Ah, yes, it's in the model here, init. So in the init package here, in the init protocol, you can see the following methods: the homogeneous environment, island environment, and remote environment. So these are the methods that I use to. I will show them to you later how it works. But basically, is the central methods that defines the initial grid. So when you open the model, you will see the grid in front of you, and it's here that I defined. The grid has 27 rows, 27 columns. The neighborhood is defined by 8 surrounding cells, and the grid is closed. The grid is not closed, which means that if you go around the edge, you get from the other side. Then you also define you initialize the initial biomass of the vegetation units or the plants, and you also initialize the agents, and you display the POV of each agent. So the POV is the point of view. So as you can see here, as you click on each agent, it has the point of view, the POV method. And for restrained forager, it is defined as blue. For unrestrained forager, it is defined as red. So basically, this point of view is basically the visual representation of the agent. And it is the interesting thing because we can add as many POVs as we want. We can define, for example, that I will show you the example, but we can define that the agent can have POV by its size or POV by its color. Maybe it can have the different POV depending on how much biomass it has. And like I showed you in my presentation, you can look at different aspects of the model. So you can look at the water in the ground or the grass, depending on which POV you select. The another important method is the control method. So if you click here on the control protocol, you will see the step method. And this method defines basically what happens at each step. So CORMAS already performs all the stepping, performs all the iterations and all the stuff. But you need to override these methods to define the specific operation that should be performed. So for example, here you see that at each step, the CORMAS will, for all entities, vegetation units, it will perform step operation, and also it will ask a random forager to perform a step operation. So actually, I think that these two lines are equivalent, so we can even rewrite them a little bit. You see it, so we can do, or not. No, sorry, I will not do this because I think that there is a difference between synchronous and asynchronous updates. So maybe the first line does it synchronously. So for example, all entities will be synchronously doing the step. And for the second part, maybe it's doing asynchronously. So at every, it will pick a random forager from each part and it will perform a step like that. But to make it more clear, because this code looks a bit confusing, so to make it more clear, I will now initialize the model. So I click initialize here, and I select this homogeneous environment. And I also select the probes. So the probes are basically the things that we want to measure. These are the special methods that we define to define measurements. So for example, in this case, we have 3 probes defined: the number of unrestrained foragers, number of restrained foragers, and amount of biomass. So we are interested in the 2, how can I select both of them? I want to select, no. Do you know how to select 2 from the spec list? Because I want to select, I can either select 3 by doing Command A, or I can select 1. Shift, okay, 1 and 2. Oh no, I still select all of them. Control, okay. 1. No, it doesn't work, but it's a mark, so it should be command instead of control. Option, okay. Let's try everything, yes. Okay, I think in this version of spec it is not working. We can only select. So like that, I will select all of them. It's better.
Oh, it's command shift.
Command shift, wow. Okay, I love old versions of spec. Okay, command shift. No. It works on my machine, right?
Then you remove one selected.
You click command for the first one, then
No.
shift, and then you click, F12 and then function.
Okay, let's stick to all of them. Okay, I select all of them. I click apply. Okay. And here you can see, okay, I will close this window here. And here you can see the space. Did you follow this process? No, okay, so I will repeat it. Yes, thank you. Did you manage to open the model like this? So do you see a SEC model written on top? Okay, great. Now you click on the button Initialize. Right? Now you select, on this side, you select homogeneous environment. And on the other side, you need to press Command A to select, or Control A to select all the probes.
You can press Shift and click on the one you don't want.
Oh, okay, let's try. No. Oh. I don't know what, I really don't know what happened, but I will not touch it. No, but I will select all of them because I want to be in sync with the others. So like that, we do the same thing. Okay, I apply. And now we have this view. Do you have it?
Yes.
Okay, great. So what this view represents? I don't know if it's visible on the screen. Yeah, I will make it bigger. Cool. So the red points or the red stars, these are the unrestrained foragers. You know, the crazy ones who eat a lot of grass. The blue ones are restrained foragers who eat moderate amount of grass. And the green is the grass. So maybe, what do you think will happen when we play the simulation? So yeah, I will show you how it is going. I press, you see this forward button, I can press step, and they're moving. You see they're moving to another location and eating grass, and moving and eating and moving and eating. And depending on how much grass they eat, they become bigger. And when they become really big, they reproduce. So they make babies. Now, what do you think will happen when we run it for 100 times? Which population will be more in a more good position? So, red, okay. Yeah, it makes sense because red they eat more, so they survive. So I play it. Yes, and you see all the red, they dominated, and then there became very few of them. So if you can click on top on the visualization here in the CORMAS, and you click on probes, you will see the chart. Can you do this? Yeah. Okay, now this part is a bit ugly. So you see the chart is working with some bugs. I will show you how. Right now you see 3 lines over there. You see the green line and the 2 small blue lines, blue and red. So the blue and red, they represent number of unrestrained and number of restrained. The green represents the amount of grass. Now we want to turn off the green. So like this, we click here and everything disappears. Why it disappears? So you need to click forward one more time and it will come back. And that happens because there is a bug that it is, you see it is not updating the row cell view when we change this thing. But I want you to do this because I want us to look at the, you see at these charts. So what we will do now, because this is, you see what happened, there was this fluctuation that the red ones were growing and then they came down. You see they started dying, right? Why did this happen? Because they ate so much grass that there was not more grass to survive. But what happens when there is no more grass is that the amount of foragers decreases. So then there is nobody else to eat the grass. So if here in the top view, you see I set 300 and I click Command S to save it, and then I continue running. And you see as I continue running, you can see these fluctuations. As it goes up and down, and I can put it even at 1000, like this. And I continue running, and look what happens. You see? So the blue ones completely died. The red ones are going up and down, depending on, you see they're kind of competing with the grass. And this is a very famous phenomenon. So in natural sciences, it's called the predator-prey thing. So you have in this case, predator is the forager, prey is the grass. So grass is trying to escape from forager. It is growing, and going down. And predator is trying to capture the grass or eat it. So predator depends on the prey. So like that, when there is no more grass, the foragers start dying. But when foragers start dying, the grass starts going up. And like that, in every predator-prey situation, there's always this fluctuation. So they always compete between themselves. There is another interesting phenomenon here is the competition of 2 types of predators. Whenever one predator eats even a little bit more than the other, it will always kill the other. So it is impossible for the other to survive if it competes with someone who eats more. It is also an interesting phenomenon. But now I will show you some interesting other example. So you can close this view. You can close, and I also recommend you to close CORMAS, like this. Because there is a very strange thing in the implementation of CORMAS that also comes from Visualworks that we're now trying to fix, is that CORMAS is really implemented on singletons. So there is a state machine that remembers really the state of the thing. And if you try to open another model, it can give you bugs because it will say, no, but I already opened the model, what do you want? So like that, you close it, you open it again over here, and you click on File to open, and again you open the ESUG model. Same way. Who is Purdue? You're Purdue? Okay, good. So now you click on initialize, but this time you click on island environment. You see this island environment. And it will give us another kind of environment. You see where the grass is separated into these islands. So you know, that's, like I told you during my presentation, this is a kind of little lab that we can play with these parameters. We can try to change the environment, play with it a little bit, and see what happens. So what do you think will happen in these islands? Will it be the same situation as before in the standard forager prey or not?
It would be harder for the red one to catch the grass because
Yes.
it's more sparse.
So how will the competition between red and blue look?
If blue is living on the island, that is good.
Yes.
And for the red one, we'll be struggling a bit with this.
Okay. Do you agree with this, or do you have other options? Okay, everyone agrees. So let's put it at 500, for example. Yes. Okay. Let's put it at 500 and let's run it. You see, yes, red killed all the blue ones. Oh no. Again, you see? Let's click one more. You see what happened? So the blue ones, they survived a bit longer, but in the end they died. Let's do it again. Maybe it's just, the simulation is like that. Let's try to run it again. So let's put initialize again, same island environment. I will make it bigger here, like this. Come down. It's stuck. Like this, yes. And I run it again. You see, the blue ones are surviving for a while. And yes, if I open the visualization, like this, the graphs. You see what happened. So now on the second run, it happened what I'm sorry, I forgot your name. Nicola, sorry. What Nicola was suggesting, that in fact, thanks to this separation, the blue ones managed to survive. But what will happen, so now another question to you. We have one more environment. So yes, and we can do one more experiment. So let's try to continue running for 1,000 steps. You see, as I run for 1,000 steps, the red ones, they still kill off the blue ones. Why? Because even if they stay in the islands, when they run out of the food on the island, they try to go outside, they travel and they find another island, and then statistically they will still kill off the blue ones. But there is one more setting that I want to show you, and those are the remote islands. So once again, maybe I can continue in the same one. I will click on initialize on the remote island environment and apply. And like this, you see, now we have these islands that are really far away from each other. So what do you think will happen on these islands? Any ideas?
At the end, I think that we will have a lot of grass first.
Okay.
The red will dominate.
Okay. So at first I will put 100 steps and I will run it. What happened? Blue. Why blue? I show the probes. Like this. Look what happened. The red one died. Why did they die?
Because they eat everything.
Yes. Because in fact, red ones, they eat everything and they don't have time to travel to the other island. It's too far. They die on the way. The blue ones, they are more, yes, they conserve more grass. They can sustain themselves. So they eat enough grass to sustain. And you can see how in this kind of environment, this animal that is sustainable, as long as there is not another animal who is not sustainable, it can survive. But if the other unsustainable animal can travel to them, they have no chance and they die for sure. So, and we can continue running it, so you see we can make.
But the point is, the red forager should have more autonomy.
The red forager should what?
Have more autonomy to go far and.
Yeah, but it does. You see that it doesn't have the time. So the red forager, when it doesn't find any food, it makes a step to the random location, then another step, and like that, step by step, it looks for food. But at every step, it loses 2 energy points. You see, so as it goes to that island, it's so far it doesn't have a chance. So you see, in this kind of scenario, traveling for food is not really an option. You can only have the food that you have near to you. In the previous scenario, the islands were closed, so you could survive as long as you were there, and sometimes the blue ones had the chance, but there was a chance that the red ones would find them. But here they have no chance to find them. And you see what happens now as I continue playing, I will put 1000 steps, and I continue playing. We have the same kinds of fluctuations, well, only on this island, so now they are small. But you see now the blue ones, they are the only dominant species, and they behave exactly the same as the red ones, except that they survive. But we have the same fluctuations, same behavior. Okay, and now the final thing that I will show you with this model is just an interesting question. So maybe you have some ideas how to save the blue ones from the red ones. Because we had once students who had an interesting idea is to what will happen. Oh no, wait, what happens? You see, I have a bug. And this, you see, this is an example of bug that we got because of the singletons. So because I didn't stop and reopen CORMAS, it remembers the previous state in which there was some application of it. So I need to. It's crazy. Okay. It's really, it's really hard because it is a legacy system that was developed. It was implemented 30 years ago. Then it was developed incrementally by adding things on top of top. Then for 10 years there was no development. And then there is ongoing migration process by copying old code in Pharo and trying to fix it. No, it was CORMAS, but in VisualWorks Smalltalk. Yes, it was implemented by it was inspired by the star logo or these original versions of logo. It was older than the net logo, than Gamma, but it was still, yes. So you see, again, I open file, open ESUG model. Okay. Yes. Then initialize, and I select the homogeneous environment, apply. Okay. And now there was one interesting idea that was proposed by one of our students. What will happen if we put, you see, we can drag and drop them. You see, and you see there is nice animation. If you drag them, they come back, right? But so if you drag them in the illegal location, so outside the grid, bam, so cool. Okay, but now we put all unrestrained foragers on one side and all restrained foragers on other side. So I will do it like that.
Can you do it when the simulation is running as well? I mean, maybe not running, but in between steps?
Yes, you can stop, you can pause the simulation. And then, well, I don't want to, okay. What I will do, I will make it simple for myself. So I close this. I open the system browser, and I change the number of foragers that we generate. So like that, it will be less. So you see, initial number of restrained, I will change it to 4. Alex. And initial number of unrestrained, I will change it to also 4. No, 4. And like this, it will be easier for me to drag them. So then I initialize again, homogeneous environment. You see now we have 4 for each type. I can start running. Then at some point I stop, and now I can drag them. You see, so it still works like this. So I drag all the unrestrained in one side, all the restrained in the other side. Yes. And I can put you remember that we have the open environment. So if they go around the corner, they will still come back. So like that, I need to put them in the center. Like this, they will be really separated. Oh no, I'll come back. Yeah, and you see this is other cool feature. If you click on anything, you inspect it. Like that, and like that. So what do you think will happen now if I play it like this? You see they're now separated. The blue ones are in the center, the red ones are far away. Any ideas? Okay. Okay, let's run it. Well, nothing changes. Sorry. No, it has no effect. But it was an interesting idea, you know, because we did it with students and they had like, yeah, let's do this. No, it doesn't help. It's a rule. They always kill them. So there is maybe one more interesting thing that I will show you is what will happen if you put 20 blue ones and one red one. So I open programming, system browser, I go to model, class side, initial number of restrained, I put 20, and initial number of unrestrained, I put 1. Okay, so we have one unrestrained. Homogeneous environment. Oh. And I run this. You see? Even one is enough to kill everyone, so it doesn't change anything. So they're still not dead, but if I continue, they will all die. Okay, so on that I finished the ESUG model, and before going, I will show you just one more model, which is very simple, but it is very interesting. So this model is called the segregation model. So as you know, I don't have slides for it because it's super simple to explain. As you know, for example, in cities, you sometimes walk on the city and you come to the super international quarter, and there's a lot of foreigners, and then you have another quarter with other foreigners. So there was a lot of social studies. So why do people get segregated in cities, and what kind of mentality causes the segregation? So there was one researcher who made he was called Schelling. So he made this model of segregation where you have, very simple, you have a city of cells. You have two types of agents. So this can be, in my model, these are green and red agents. And each agent is very, very open-minded. They're super fine to live with other types of agents. The only thing they want is that 30% of their neighbors are of the same type. You know, so that's not much to ask, because they accept that the majority of their neighbors are of the other type. They're foreigners, they're from another ethnicity, another culture, but they're at least 30% are their own culture, because like that they don't feel lonely. So we think this is something normal. This is something not, you know, not racist, not bad, not chauvinistic, but still we will see what happens. So for that I need to open Iceberg again. I click on plus, clone from GitHub. We write CORMAS here, not French, English, CORMAS, yes. And we write shelling model. And be careful, because normally shelling is written SCH, but unfortunately I call this repository incorrectly. So please write it like this. SHELLING model. Okay. Now you click on OK. So did you write it? Because I leave it on the screen so you can write it correctly. Yes. Let me know when you're done. Good. Cereal. Okay. I have time to drink water. Good. Cereal? Not yet. You sure? Oh no, okay. Okay. So like that I load, and we have, okay, then again I go down in the list, I double click, and I select the package that I want to load. Wait, double click, this is a bad table. Yes, double click, then right click on this package and click load. Good. No, no, don't do this, no, close. Okay. Now I open CORMAS, file, open, and I have the shelling model here. I click on shelling model, I click on OK, and I have it here. Do you have it? Great. Now I click on initialize, I select the only init method, because it's the only one, and apply. And now we have this kind of city. You see? So I will explain a bit the scenario. So these green and red stars, those are the two types of groups. So ethnical groups, I don't know, language groups, anything. The little stars are the ones that are not happy. The blue stars are the ones that are happy. So you can imagine these are two groups of people. So during my last presentation, I said these are Argentinians and Ukrainians, because we are not comfortable to live too close to each other. Like Argentinians are usually very loud, they sing songs, and Ukrainians, we like to be in quiet environment. So like that, you see the green ones, that the small ones there, they're small because they're not happy. They're surrounded by too many foreigners. And the other ones, they're happy. So every time on every step, the unhappy agent tries to relocate to any available cell on random. So they randomly pick any other location, so they change the apartment. And you see, I click here, play, here. And just in 3 steps, 4 steps, bam, we have super segregated city. You see, so that experiment, it shows that segregation doesn't come from really like deep hatred. It often comes from just a small desire to be next to the people of your own culture. So it already is capable to create segregation. And we can play with these parameters because we can change something. So, well, in this simulation, there is not really much we can change, but what we do change, we can change the there is a parameter which is called the percentage of people of your own culture that you want to live next to you. So right now it is 30%, as in the original model, and we can change it to become smaller. For example, what happens if you make it 20%? So I go to shelling agent in this case, class side, and percentage of similar agent, I put it 0.2. So like that, it will be 20%. Then I reinitialize the model, apply, and we play it. And you see, with 20% is fine. There is not that much segregation. There is still some, but not that much. So 30% is really this. Okay, you see? Yep. Okay, I do command dot. Hopefully it works. Yes. And now Milton showed me a super nice trick today, which I didn't know. Yes, you click here, close all, Windows to the right. Ha, magic, right? I didn't know that. Oh no, they're still coming. How do I kill Cyril? What is the dot command? Do you remember? Command dot. Close the image. Yes, thank you. Okay. Okay. Well. Oh, maybe yes. Maybe that's a good idea. Okay. Yes. Yes. Perfect. Let's try to open it again, if it will work with the same parameter. Yeah, but I will, so you already saw the 2, but I want to show you now the bigger parameter. So let's say we put 0.6, like really, in this case, the population wants to have the majority of neighbors of the same culture. So we will see the amount of segregation that it produces. So shelling model, okay. And then we, okay, so you see, in that case, if the visualization did not open, we can click on visualization. And by the way, I don't, Why? Yes, you click on space, and then you click on POV. I don't know. You see, okay, now something is broken because it is not opening at all. So let me close this. Ah, okay. Open again. Shelling model. Okay. Initialize, init. Apply. Ah, yes. Okay, perfect. You see, so now when I open this simulation again, like this, you see what happens is now the majority of agents are not happy. Almost all of them are not happy because they're randomly initialized and randomly majority of their neighbors are not their own. So if I click to play, wow, you see they get segregated into really, really big group. And even they try to make some border between themselves. So they try to leave this empty space between them so that not even to see the other people. Okay, that's the kind of model that we have. So that's all that I wanted to show you today. So the two models and how we can play with them, how we can manipulate the parameters. So thank you for your attention. And I would be happy to hear your feedback about that as well. So maybe you have, by the way, maybe we can use some, because we have still some remaining time. I think we have 3 minutes remaining before it is a complete hour. So maybe you can share with me some feedback because, for example, yes, it is obvious that CORMAS right now, it is in a beta version, it has a lot of bugs. But despite that, I'm interested to hear your opinion on the user friendliness. For example, the way that we do things, the way that the interface is working. So maybe you have some suggestions on what would make it more approachable, what would make it more user-friendly, and maybe until next ESUG we could have these improvements already implemented. So, yes?
I wonder, it's my moose bias, but has anyone used a moose model to evolve and using that way?
Oh, that's such an impressive idea. Yes, I would love to do that. No, nobody did that. Nobody did that. Nobody did it, but it would be super nice to. So you mean to use moose model as?
So I was thinking, like, you do a moose model for every version of a file in a
Yes.
GitHub, and then so your steps would basically be loading the changes of the code or something.
Oh, okay.
I haven't figured it out yet, but I was
Yes,
thinking,
yes.
once you have the step.
Yeah, and then the agents. No. To make it quick, I will say no. Nobody did it, but it would be super interesting to explore these things. Yes.
Just because of the history part, that's the part I think is interesting.
Yes. Yes, indeed.
And also the visualization here, it's a rectangle, but you could do any visualization.
Yes, in fact, so this is also an interesting point. So very popular type of visualization are, so they're rectangular grid, but there are also hexagonal grids, where each cell is a hexagon. So we were discussing this with Milton today, and hopefully we will be able, to implement it in the near future. But right now, Milton showed me super nice examples of hexagonal visualizations, of hexagonal layouts, but it still needs to be implemented in raw cell as layout, because right now it's just you need to manually align things in hexagonal positions. But yes, and then in that case, it would be very interesting to see, for example, maybe you can have either, like a hexagonal combination of these hexagons, or maybe square combinations of hexagons, or maybe even something, user-defined, where you can say, I want this kind of polygon of hexagons. Yes. Yes?
Not about the software, but about the modeling.
Yes?
I think it's very sensitive to having the right model and not to make failure in that. And because otherwise you get results and you think, oh, it's like this or like that, but you maybe made a failure in the model. How much work do they do for the right modeling, your colleagues? Do you know that, or how they check if they model it right? What they
Okay, I will try to repeat this question, so tell me please if I got it correctly. So the question was, how do people who use this kind of modeling, how to make sure that the parameters of the model are correct? How do they make sure that the model is defined in the right way? Is it correct?
Yes.
Okay, thank you very much. So in fact, as I mentioned already in my presentation yesterday, the goal of this kind of modeling is not to reproduce the world in a realistic way. It's not to have the actual correct representation of the world. We rather want to, encourage people to discuss. So this kind of process that we had today, especially with ESUG model, when we were, making theories, why is it working like that? Why is it not working like that? What would help it to work in another way? So is this part that is important. Now, after that, foragers ate 50%, one forager ate 50% of the grass, another one ate 99%. And are those numbers correct? Probably not. They don't represent real animals. But they do encourage real discussion that represents certain social phenomena, that represents certain natural or social practices that we want to explore. So like that, again, the goal is to encourage communication. That's the point. And that's why in this kind of tools, what's really important is to have the possibility to change parameters quickly. Normally, this is something I didn't want to show because it is buggy, but if you click here, you have the class for each entity. So for example, here you have, in this implementation, for example, for the segregation model, I call them frog and turtle. So instead of being people, I say, we have frogs and we have turtles. So here you can see, for example, shelling agents, shelling frog, shelling turtle. And if I click on any of them, I'm shelling cell. If I click on any of them, I can edit attributes. And here we have the UI to edit the attributes. And you can click on the attribute and then change the parameters, change the values. But you see, I didn't show this way of manipulation because there are some bugs in the UI. But normally, this in VisualWorks version of CORMAS, this is part of the process. So that normally, as people discuss, as they want to try different versions, they need to have a quick way to change something. And we have also some nice idea that, for example, right now when you click on each agent, you click it here, like BAM, and you have an inspector. And this is a super nice thing because when I show it to my modeling colleagues, they really love it because in other platforms, it's something that doesn't happen. You cannot really manipulate individual agents. You cannot really click on them. Here you see this is a specific turtle. And I can send comments to the specific turtle. I can make it die. I can make it move somewhere. What I want to implement is when you click on it, you actually have the visual inspector where you have the small picture of this turtle, when you have the parameters, the UI that allows you to change these parameters. So like that, it would be much more fast and much more easy for people without touching the code to manipulate the model. Yeah, and to highlight also, because right now, I'm inspecting the model turtle, and we don't know which one. So that's a very good point. Yes.
Is it possible to launch a campaign of simulation, like, or you put interval of variables and batch? I don't think so. That's maybe something.
Yes. Yes, so the question was, would it be possible to launch a campaign of simulations? So when, if I understand correctly, well, multiple simulations are running at the same time and communicating between them.
No. There was another question. One after the other one, but with different parameters.
Oh, yes, okay, that's a super good question, thank you. So as you saw, we were looking for the value of the parameter that was optimal. So when we were doing this, for example, with segregation, we were seeing that at 30% there is visible segregation, and at 20% the segregation does not happen. So how do you find this parameter that is optimal? So for that, there is the kind of analysis when we define certain grid of parameters, and then we run the simulation again and again and again on each value, and then we get the result. So right now, we can do this easily by making a loop. So we just set of parameters run simulation. However, we have an ongoing work to support the OpenMol. And OpenMol is a special platform that uses a server. We represent Pharo image as a Docker file. We send it to this OpenMol. We define a set of parameters. And then on some distributed servers, they run it many, many times. And they produce a super nice analysis. And it's the same platform that is used for NetLogo, Gamma, for Java, for many other applications. So in those research communities who use modeling, they're often they like to use tools like that. They like to use OpenMol because it also produces them scientific reports, with the specific values that they need to publish this. So we also, yes, we can do a loop, we can do this manually, but we also try to support this kind of bigger platforms for that. And that's it, or I think, yes, there was a question there.
I was thinking, you remember when we put all the red and blue stuff?
Yes, on the sides.
Is it possible like to save a configuration manually so we can replay it easily?
Oh, yes, yes, indeed. Right now, I think it is not possible, but it was possible for sure. Because as I mentioned yesterday, there was a possibility, in Visualworks version, there's a super nice feature to replay the history. So each point of the history, each configuration, it is stored.
In a user experience way, I think it would be nice, I don't know if it's possible not to, like you save the configuration in the file at some point, and to load it, just like drag and drop inside the Pharo image, and so.
Oh, yeah. That could be cool, yes. So you mean to save configuration separately from the model itself?
Yeah.
Okay.
So you can drag and drop and easy to start and start.
I will look into that. Okay. Thank you very much. Okay, thank you. If there are no other questions, I think it is time for us to go home. Thank you.